So today we're going to move on to a new lecture. This is going to be lecture 18, coordinates and basis. Okay. Again, we are still working with something quite abstract compared to all the materials that we cover in the past. Okay, especially for computer science students or non-math major students. But this is very important idea even for us as computer science majors. That's because when you look at certain things, you need the informations of coordinates and basis. So I'm going to bring up some examples, real-life example that relate the topics of coordinates and basis to those real-life example, and then we're going to dive into the theory, and hopefully we could be able to capture the essence of coordinate and basis. All right, so why do we need coordinate and basis? Now, when we look in the world and you need to describe certain movement of the weather, right? You need to describe that how the wind going to blow in certain directions, or how you travel from one point to another point, right? And how would you describe that using the directions that you are going? So thinking about, okay, when you look at the map, when you look at certain directions, you have four main directions, right? So you have east, you have west, you have north, and you have south. Okay, that's the basic information that you need to agree on, that we all need to agree on, that when you look at the map, those are the directions that you can describe and everyone understand what you are talking about. Okay, and based on those information and based on those direction, now you can describe certain thing, right? You can describe the northeast direction, you can describe the northwest directions, so on and so forth. Okay, so that is important, right, for the real life situation, not only for mathematics, but also for physics, computer science, geology, geography, and other sciences as well. In addition to that, we are related to computer science to help us design certain things, right? So when you talk about computer graphics, you can talk about game designs. Of course, you don't look at the game in terms of the 3D things that we see in reality. You need to design their own coordinations, okay, and different point of view, right? If you play Call of Duty, you have a different point of view. If you control a Mario Kart, you have a different point of view, right? And because of different point of view, then now you need a different coordinate system. And with different coordinate system like this, you need a different basis, right? For our 3D view, we need X direction, Y direction, and the Z directions if you don't count time, so it's just three-dimensional space. And you look at the unit vectors, you have I, J, and K. Now, when you design the game, you base on the real-life situation like that, and you develop a character coordinations. And with the character coordinations, you also need to pull in some unit vectors and call them the basis, right? And based on the basis of vectors, you can design the game more appropriately and more realistic, right? So that's one way to look at basis and coordinates. Another thing is that if you are into robotics, you need to design robots, right? What's going to happen when you design the joint on the arm of the robot? You need certain coordination. Because not only you have this type of movement back and forth, up and down, but also sometimes the robot can rotate like this. Right? So you don't have to do this for game design if you have the character just moving up and down, left and right. But with the robot, you want to mimic the certain motions or human motions that you need to design a basis and the coordinations for the arm of the robot. Now, another example I want to bring up is, again, I'm kind of into computer things. Now, for the computer visions, right, when you wear on the virtual reality classes, you can have a different point of view, and you can look up, you can look down, you can move sideways, and anytime you move that, the screen also move with you, right? Or you change the point of view, and those are not our point of view in real life, but actually the point of view from the virtual reality. And in order to build up those virtual realities, then you need coordinations and basis. Again, coordinations tell you where to go. The basis tell you that what type of vectors that you are dealing with. Of course, coordinates and bases are used in machine learning and data science, but those concepts are a little bit more advanced compared to us, what we are covering right now. So I just want to mention that, okay, they are used in machine learning, but we're not going to see that directly, but as a foundation for other more advanced topic in machine learning. But if you are computer science and you decide to go with to be a web designer, working with database, or just a standard software engineer, and not a game developer, then this is probably not a topic that you really going to use a lot. But with the development of the world right now, gaming design, graphic design, computer vision, robotics, and simulations are very important, and they use a lot of this information of coordinates and bases in their work. All right, so hopefully that captures some of the applications of coordinates and bases. Okay, so on this topic, on this lecture, hopefully you could be able to understand the definition of a basis for a vector space. We already talked about the vector space last week. So vector space, the collection is the space of vectors, the collections of vector. You assign on a space, you have infinitely many points, and on each point you assign a vector. And in a vector space, you can have a couple of a set of scalars and a set of operations. Now, in vector space that we are dealing with, you have operations called vector addition and scalar multiplications. Okay. You can add vectors and create new vectors. You can scale vector to create new vectors as well. Right? Those are, again, vector addition and scalar multiplications. Now, for vector space, you can have a basis that create those vector space. For example, two-dimensional plane, you have I and J. Those are the basis of the two-dimensional plane. In three-dimensional space, you have I, J, and K. Those are the basis of a three-dimensional vector space. And I, J, the set of I, J vectors and the set of I, J, K vectors are called the standard basis. Now, when you can find a different set to be a basis for a vector space, those are called the non-standard basis. Okay, we're going to look at the definitions, the theory of a basis for a vector space. So let's talk again the theory of the coordinate system. Right. So if you take, or if you have taken college algebra or pre-calculus or even calculus, you get to know the coordinate system. Right. You have the XY coordinate system. You have the X, Y, and Z coordinate system. So this is called the rectangular coordinate system because you can find a point here, and on the point you can project that, and from the point you can project that onto the x-axis, onto the y-axis, and you can see this is the rectangular shape, and therefore the name rectangular coordinate system. You can do this for the case of two-dimensional plane. So this is two-dimensional plane, and this is three-dimensional space. Okay, so this is on theory that we always use this type of coordinate system to describe a point. Okay, but it's not necessary. It's not always like that. Right? When you design a game, when you design virtual reality, you don't have this kind of luxury to just have rectangular coordinate system. A lot of time, many times actually, you need to use something called the non-rectangular coordinate system. Right? Now, in 2 space and 3 space, the points can be described using a non-rectangular system like this, or in this case, and in the 3-dimensional space. Most of the time, or at least in linear algebra, the coordinate system are commonly specified using vectors rather than coordinate axes. Right? You can describe vectors using the component form or the standard unit vector form. Right? So let's say give me the point 4, 3. Let's say you have a vector equal to 4, 3. So this vector is written in the component form. Now, most of the time, this vector is written in form of standard unit vector I and J. Okay. And this coordinate system is described under a vector rather than a coordinate axis. Right? So I is a vector 1, 0. J is the vector 0, 1. Now, when you do cross product, usually we get the answer in the form of standard unit vectors. Okay, so the vector we obtain are described under the idea of ordered vectors, or in this case, the standard unit vectors. Let's say instead of using the point P equal to A comma B, you can describe this point in terms of vectors. Right? So you have the initial point at the origin and terminal point, which is the point P equal to A comma B. And the vector OP, in this case, is equal to A times U1 plus B times U2. So the vector OP is described using all the vectors, in this case, vector U1 and vector U2. Okay. You have a set of vectors, U1 and U2, and you have a set of scalar A and B. So A multiplied with U1, B multiplied with U2, and the resulting vectors AU1 and BU2 are added together. So in a way, this is a representation of a vector space, right? You need a set of vectors, you need a set of scalar, you need some operations, you have vector additions and scalar multiplications. Okay. Now you can do this something similar in the case of three-dimensional space, right? So in this case, you have the point in space. The point P is equal to A, B, and C. So OP in this case is described using A times U1 plus B times U2 plus C times U3. Okay, so again, this vector is the representations of the vector space. Right? You need a set of vectors, you need a set of scalar, you need vector addition, and you need scalar multiplications. So in this case, we don't have a regular rectangular coordinate system. You have some different system, different coordinate system that help us describe a directions. In this case, a vector OP. Okay, and we no longer use the standard unit vectors U1, U2, standard unit vectors I, J, and K, but we use some non-standard unit vectors U1, U2, and U3. However, this U1, U2, and U3 is going to be the vectors in the basis of the non-standard or the non-rectangular coordinate system. Okay, so that is the essence of the definitions of basis. So I'm gonna start writing down definition again. This is quite abstract, so let me know if you have any questions on this, okay? And also slow me down if you think I'm going a little bit too fast. So let's say you have a set of vectors. Again, the set is the collections of elements. So you have this set, you have a collections of a bunch of vectors, basically n vectors in the vector space V. And this set is a basis for V when the following conditions hold. Okay, so the first condition is going to be S spans V. Right. With this set, you can create all of the vectors inside the vector space V. Right. So what type of S that you have seen before? Right. So you have the set of the standard unit vectors I and J. Okay. So let's say you have S is equal to 1, 0, and 0, 1. So this is the set of the standard unit vector I and J. With these two vectors, you can describe or you can generate all the vectors in the vector space R2. Okay. And so S is a basis of R2. All right, we get to that later. But the first conditions that need to hold that S spans V. And S is linearly independent. Okay. So quick descriptions on the first conditions that S spans V, that is for any vector V in capital V. The vector V can be written as a linear combination of V1, V2, up to Vn. Okay. So again, we did the problems related to this first condition already last week. That is, so to see S spans V or not, you choose any vectors in the vector space V, right? And then you can check if V can be written as a linear combinations of the vectors in S. If that is the case, then you say S span V. Okay. Now for the second condition, I have a quick description here as well. For S is linearly independent, that is the linear combination C1V1 plus C2V2 plus dot 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 up to Cn Vn is equal to 0 vector, and this holds when C1 equal to C2 equal to C3, so on and so forth, up to equal to Cn, and this is going to be equal to 0. Okay. So you need to check these two conditions. We're going to do that. We're going to do some example to see that. But there are two conditions to check if a set represents A or is a basis for a vector space. The first condition is that S spans V. The second condition is that S is a linear independent set. All right. Some remark here I want to give you is that if a vector space V has a basis with a finite number of vectors, then V is finite dimensional. Okay. So an example I give you here, S is the set with two standard unit vectors, and this set is a basis for R2 because there's only two vectors in the set, right? And this set creates or is the basis for it. Otherwise, V is infinite dimensional. So let's consider the following example. So the first example is that can you show the set S to be a basis for a two-dimensional plane? Okay. So this is the set of standard unit vectors I and j, and we need to check two conditions, that S spans V and S is a linearly independent set. So the first thing that is, so the set S that is equal to the vectors 1, 0, 0, 1 spans V, in this case R2, because any vectors U equal to U1, U2 in R2 can be written as, so U1, U2 is equal to C1 times 1, 0, is equal to U1 times 1, 0 plus U2 times 0, 1. All right. Or you can write U is equal to U1i plus U2j. Okay. So we check the first conditions, that is the set span R2. Okay. Now the second condition is that S is linearly independent. So the set S is also linearly independent because the equation, you have the following equations, that is C1 times I plus C1 times I plus C2 times j equal to 0, right? Or C1 times 1, 0 plus C2 times 0, 1 equal to a vector 0, 0. Right? So this system has only trivial solutions. Now you're going to see that you can rewrite this equation as, take a look at the first component. Right? For the first component, you have C1 plus 0 C2 equal to 0. So C1 plus 0 C2 equal to 0. This implies that C1 is equal to 0. Now for the case of the second equation, you look at the second component. So C1 times 0 is 0, right? Plus C2 equal to 0. So 0 C1 plus C2 equal to 0. This implies that C2 is equal to 0. So the equation only has trivial solution. Okay. So this implies that C1 and C2 equal to 0. Then by definition, S is linearly independent. Right, so you check two conditions. You have a set of vectors, and this set span R2, in this case, is R2, and the set is also linearly independent. So you check two conditions. Now you can conclude that S is a basis for R2. Therefore, S is a basis for R2. All right. Technically, there's a name for this because set S is the collection of standard unit vectors. The set S is called the standard basis for R2. So, or S is a standard. So is the standard basis for R2. Okay. Now we're going to do the same thing for the case of the three-dimensional space. You have a set of three standard unit vectors I, j, and k, and we're going to go through the process again to check if the sets span R3 or not, and if the set is also linearly independent or not. Okay, so let's move on to example 2. So in example 2, you have a set of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this set is the spaces for R3. And we're going to show that that is the case. So this is I, this is J, and this is K. Okay, so the set S is the set S spans R3 because for any vector U equal to U1, U2, U3 in R3, the vector U can be described as, so U is equal to U1, U2, and U3. This can be written as U1 times 1, 0, 0 plus U2 times 0, 0, 1. Sorry. U2 times 0, 1, 0 plus U3 times 0, 0, 1. Okay. So U can be written as linear combinations of the vectors in S. In this case are I, J, and K. Okay, so therefore S span R3. Okay. In addition, S is a linearly independent set. In fact, consider C1, C2, and C3 such that C1 times I plus C2 times J plus C3 times K equal to the 0 vectors. And from here, we're going to show that C1, this equation is true only when C1 equal to 0, C2 equal to 0, and C3 equal to 0. So C1 times the vector 1, 0, 0 plus C2 times the vector 0, 1, 0 plus C3 times vector 0, 0, 1. This is equal to vector 0, 0, 0. So you have a vector with 3 components, therefore it's going to give you a system of 3 equations. So let's take a look at the first component. So we obtain. So the first component gives you C1 plus 0 C2 plus 0 C3. It's going to be equal to 0. So C1 plus 0 C2 plus 0 C3 equal to 0. So this implies that C1 is equal to 0. Now for the second equation, which is the second component, you look at the second component, you have 0 C1 plus C2 plus 0 C3 equal to 0. So 0 C1 plus C2 plus 0 C3 equal to 0 implies that C2 is equal to 0. Similarly, for the last equation, you have 0 C1 plus 0 C2 plus C3 equal to 0. This implies that C3 is equal to 0. Right. So C1 equal to C2 equal to C3. So this indicates that S is linearly independent. Okay, and you can conclude that therefore S is the basis for three-dimensional space or R3. More specifically, S is the standard basis for R3. Okay. You can play the same game for the case of S with four vectors. Let's say 1 0 0 0, right? 0 1 0 0, 0 0 1 0, and 0 0 0 1. Right? In that case, S is the standard basis for R4. Okay. Now, generally, the vectors E1 equal to 1 0 dot 0, comma E2 equal to 0 1 0 dot 0, and you do this all the way to En equal to 0 0 dot 1 in Rn forms the standard basis for Rn. Okay, so that is the general implications of standard unit vectors in a set that help create a standard basis for Rn. So this is standard unit vectors, this is standard basis. So let's go back to the idea of standard basis. Right? So with the standard basis, that help you form a rectangular coordinate system. Right? So in the case of two-dimensional plane, you have I moving in the positive x directions, you have j moving in the positive y directions. And in the case of three-dimensional space, we also have a standard basis, right? It's a set of three vectors, I, j, and k. Again, I is a standard unit vector in the positive x directions. J is the standard unit vectors in the positive y direction, and k is the standard unit vector in the positive z directions. Now, as I mentioned earlier, most of the time, this is what you see. You see the rectangular coordinate system. But in practice, not always that is not always the case. A lot of time, you need to use non-rectangular coordinate system in 2 space and in 3 space. Okay, so that is you no longer need a standard unit vector, so you no longer need the standard basis. Now you're going to develop or form certain things called the non-standard basis. Okay, that is example 3, right? A non-standard basis for R2. Now you have this set. This set is the set of 2 vectors, 1, 1, and 1, negative 1. Okay. To see if this set represent or form a basis for R2, what you need to do? You need to clarify 2 conditions. You need to check that if S span R2 or not. And the second condition is that can you determine if S is linearly independent or not? If that is the case, then you can conclude that S form a basis, right? In this case, of course, it's a non-standard basis for R2. Okay, so I break it out into 2 different questions here. The first question is that can you show that S spans R2? And the second question is that can you determine whether the set is linearly independent or linearly dependent? Okay. So let's check the first question. So to show that S spans R2, we need to show that for any vectors U equal to U1, U2 in R2, U can be written as a linear combinations of V1 and V2, where V1 is equal to 1, 1, and V2 is equal to 1, negative 1. Okay. So that is we're gonna do some calculations here. Okay. So we have C1 times V1 plus C2 times V2 equal to U. So in this case, we need to show that U could be able, or U can be written as a linear combinations of V1 and V2. Okay. So V1 is equal to 1, 1. V2 is equal to 1, negative 1, and U is U1, U2. So from here, you're going to obtain a system of 2 equations because the vector has 2 components, and that's why you have that's why you have a system of 2 equations. Okay, so for the first component, so we obtain from the first component, you have C1 C1 times 1 give you C1 plus C2 equal to U1. So C1 plus C2 equal to U1. Now for the second component, you have C1 minus C2 equal to U2. Okay. So we have seen this type of issues before, that on the right hand side there are no specific values for you to calculate, right? Usually what we do to solve the solution of the system is that you can turn this into an augmented matrix. We use the code, Python code, to give you the answer. Right? However, again, on the right hand side, there's no specific values for U1 and U2. Therefore, you cannot follow that approach anymore. What you do is that just look at the coefficient matrix and check the determinant of the coefficient matrix. Okay, so from here, the coefficient matrix is A equal to the matrix of the form 1, 1, 1, negative 1. And you just need to determine the determinant of A. Right. If the determinant of A different from 0, then you can say that the system has a unique solution. So let me go back to the properties of determinants. So this is in lecture 10, right? Theorem 5. So you can check that A is invertible, implies that the determinant is different from 0. Now with the determinant different from 0, you have an equivalent statement that A system here has a unique solution. Right. So we don't need to specify any values for U1 and U2. We don't even need to find the specific value or explicit value for C1 and C2. We need to check if the system has a unique solution or not. And in this case, you can do that by checking the determinant of the coefficient matrix A. So the coefficient matrix is of the form 1, 1, 1, negative 1. And the determinant of A, right, so this is 2 by 2 determinant. So the determinant of 1, 1, 1, negative 1 is actually equal to negative 2. How can I know that? So you take the product of the main diagonal, which is 1 times negative 1 is negative 1, minus the product of the off diagonal. So that's why you have the determinant to be negative 2. And this is different from 0. Right? When the determinant is different from 0, you can conclude that. So this implies that the system has a unique solution. Thus, the vector of consideration in this case, U can be written as linear combinations of V1 and V2. Therefore, you have S spans R2. All right. So with all of this work, we just show that the set S consists of 2 vectors, 1, 1, and 1, negative 1 spans R2. Now, the second conditions that you need to check is that can you determine whether or not the set is linearly independent or linearly dependent? Okay. Now, to determine whether S is linearly independent or not, we do the following. So we form an equation. C1 times V1 plus C2 times V2 equal to the 0 vector. Right? So by definitions of linearly independent, let me go back here to the descriptions. That is, so S is linearly independent if the vector in S can be written as linear combinations, and that is equal to 0 vectors. And this equation only holds when C1 equal to C2 equal to C3, so on and so forth, equal to 0. Okay. So you have this equation, C1 times V1 plus C2 times V2 equal to 0. So you know the value of V1, which is 1, 1. You know the value of V2, which is 1, negative 1, this is equal to 0, 0. And from here, you can obtain a system of equations again. So we obtain C1 plus C2 equal to 0. C1 minus C2 is also equal to 0. And again, you can solve this by hand easily. Right? You can use elimination method, substitution method. Now on the right hand side, you know the specific value. You can turn this into an augmented matrix. let run the code, and you get the answer that is C1 equal to 0 and C2 equal to 0 as well. But also you can use the fact that we get up here, that is the determinant is equal to -2. We have a few equivalent statements that we see earlier when the determinant is different from 0. So when the determinant is different from 0, you have an equivalent statement that is A is invertible, but also you have a unique solution for this type of system. And we use this fact in the first part of the problem. Now, for the second part, when you have a homogeneous system, that is on the right-hand side, you have a 0 vector. You can use the fact here. That is, the homogeneous system has only trivial solutions. So in this case, C1 is going to be equal to 0, C2 is equal to 0, right? So you don't have to do the calculation, you just need to apply the conditions or equivalent statement for a non-singular matrix. Okay, so let's go back to our problem here. Since the determinant of A or the determinant of 1, 1, 1, -1 is different from 0, we obtain the trivial solution, or C1 equal to C2 equal to 0. This implies that S is linearly independent. Therefore, S is a basis for R3, sorry. So that is example 3. I'm going to move on to example 4. So in example 3, we have a set, and we show that this set formed a non-standard basis for R2. In example 4, we have a set consists of 3 vectors, 1, 2, 3, 0, 1, 2, and -2, 0, 1. And we're going to follow kind of the same procedure to show that this set is going to be a basis for R3. So again, we're going to show that S span R3, and then later we're going to show that the set S is a linearly independent set. Okay. So to show that S spans R3, we need to show that for any vector U equal to U1, U2, and U3 in R3, U can be written as a linear combination of V1 equal to 1, 2, 3, V2 is equal to 0, 1, 2, and V3 is equal to -2, 0, 1. Alright, so then you have C1 V1 plus C2 V2 plus C3 V3 equal to vector U. Alright, so you know the value of V1, you know the value of V2, and you know the value of V3. Okay, U is written as U1, U2, and U3, so substitute those information into our equation. You get C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times -2, 0, 1. This is equal to U1, U2, U3. And from here, we obtain a system of 3 equations. So we obtain. So the first equation, you have C1 plus 0, C2 minus C3 equal to U1. In the second equation, you choose you obtain, or you combine the values from the second component, that is 2C1 plus C2 plus 0, C3 equal to U2. And for the last equation, you look at the third component, that is 3C1 plus 2C2 plus C3 equal to U3. Again, this is the issue we have seen before, that is, there's no specific value on the right-hand side of the equations. So you just need to use the coefficient matrix and to check the determinant of the coefficient matrix. So from here, you get the determinant of 1, 0, negative 2, 2, 1, 0, 3, 2, 1. All right, so you need to calculate the determinant of this 3 by 3 matrix. Okay. I don't, can you let me know, like, did I show you how to do or how to find the determinant using code, using Python? So here the code, right? So import numpy as np as always. You're gonna form a coefficient matrix. So in this case, going to be different from what you see on the screen now. Okay. And we're going to use np.linalg, which is stand for the linear algebra package, and the determinant is just det, right? Stand for determinant. So let me get this out of the way. So you have a 3 by 3 matrix. So let's form that. The coefficient matrix is 1, 0, negative 2. The second row is 2, 1, 0. The third row is 3, 2, 1. Right, so you run the code and you get that the determinant is equal to negative 1. For someone wonder what is going on here, you can just either you print results and you get the result here as negative 0.9999, and technically that's negative 1, right? Or you can round off all the decimal places up to just 2 decimal places. So we are using something called fstring, right? Where you have the result and you just minimize the number of floating point up to just 2 decimal places to get negative 1.00. Okay. So either one should be fine. That's going to give you the answer, which is negative 1. So the determinant in this case is negative 1, which is different from 0. And from here, you can just conclude that there's a unique solutions to the system. And therefore, you can be written as a linear combinations of V1, V2, and V3. So since the determinant of A is different from 0, the system has a unique solution that this implies that S spans R3. Okay. Now we're going to move on to the second part of the problem that we need to show that S is linearly independent. Okay. So to check, or to show whether or not S is linearly independent, we do the following. So we have C1 times V1 plus C2 times V2 plus C3 times V3 equal to 0. Okay. So from here, you again substitute all you know into the equation. So you know V1, V2, V3, and opposed to 0 vector. So C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 2, 0, 1, which is equal to the 0 vector. Okay, and again from here you're going to obtain a system of linear equations of the form C1 plus 0 C2 minus 2 C3 equal to 0. The second equation is 2C1 plus C2 plus 0 C3 equal to 0. And the last equation gives you 3C1 plus 2C2 plus C3 equal to 0. And again, you don't have to follow all the calculations to get the value of C1, C2, and C3, you just basically use this fact right here, that is the determinant of the coefficient matrix is different from 0, right? That implies that this system has a unique solution, okay? And in addition to that, when determinant is different from 0, right, the determinant of the coefficient matrix is different from 0, this system has a trivial solution, right? It has a unique solution, and that solution is a trivial solution. So since determinant of A is different from 0, we have C1 equal to C2 equal to C3 equal to 0. This implies that S is linearly independent. Therefore, S is a basis for R3. So we just use a bunch of examples to show if a set S is a basis for a vector space, right? You can have standard basis or you can have non-standard basis, right? Whatever the case, you just have to show that the set satisfies two conditions, right? The first condition is that S spans the vector space. That is, for any vector in the vector space, that vector can be written as linear combinations of all the vectors in S. And the second condition is that S is linearly independent. Right? So you need to check that a linear combinations of the vectors equal to the 0 vector only holds when C1 equal to C2, so on and so forth, equal to 0. So two conditions that we need to check. And we did 4 examples, right? The first 2 examples are on the standard basis, and the next 2 examples are on the non-standard basis. All right. So if S, we have a theorem here that is the uniqueness of the basis representations. So if S is a bunch of vectors, v1, v2 up to vn is a basis for a vector space, then every vector in V can be written in one and only one way as linear combinations of vectors in S. Okay. So we're gonna go back after the break and to talk about example 5. Right. So example 5 is going to be used to illustrate the fact that there is only one way to write linear combinations of vector in the vector space from the vectors in the set. Okay. I'm recording. All right, so the theorem that we're going to look at is the uniqueness of basis representations. We're not going to prove that, but we're going to work on an example very similar to what you have seen before, just to show this is kind of like the different perspective on the procedure that we did in the first 4 example. So we're going to show that the equation, which is U equal to C1 V1 plus C2 V2 plus C3 V3, has a unique solution for the basis. And the basis in this case is S equal to 1, 2, 3, 0, 1, 2, and negative 1, 0, negative 2, 0, 1. All right. So suppose U equal to U1, U2, U3 is in R3. Okay. U then U can be written as a linear combination of V1, in this case, is equal to the vector 1, 2, 3. V2 is equal to 0, 1, 2. And V3 is equal to the vectors negative 2, 0, 1. Okay, so now the vectors, you have a linear combination, right? So that is, so C1 times V1 plus C2 times V2 plus C3 times V3 equal to U. So you know the value of V1, V2, and V3. You also know the representations of U, which is equal to U1, U2, and U3. in this case, it should be the parenthesis, not bracket, curly bracket. All right, so C1 times the vector 1, 2, 3 plus C2 times the vector 0, 1, 2 plus C3 times the vector negative 2, 0, 1. This is equal to vector U1, U2, U3. All right. From here, you can form a system of linear equations. We obtain C1 plus 0, C2 minus C2, C3 equal to U1. The second equation is 2C1 plus C2 plus 0, C3 equal to U2. And the last equation is 3C1 plus 2C2 plus C3 equal to U3. All right. And again, in this case, you don't have any specific values for U1, U2, and U3. What you do is that you just need to form a coefficient matrix. Find the determinant of the coefficient matrix and make sure that the determinant is different from 0. When the determinant is different from 0, you can conclude that the system has a unique solutions, and therefore it helps answer the questions that, or is help illustrate the fact that, when you have vector in a vector space, and that vector can be written as linear combinations of all the vectors in S, and therefore that linear combination is a unique linear combination. Okay, so let's form a 3 by 3 determinants. In this case, you have 1, 0, negative 2, 2, 1, 0, and here 3, 2, 1. So this is 0. And you go to Python again, and you see that we already did this problem we already did this in the last example with the exact same determinant, right? So the same coefficient matrix. Now, as I mentioned a little bit earlier, that is very similar to the procedure in the first 4 example. It's just we look at it differently. So in this case, give you negative 1, different from 0. So since the determinant of A is different from 0, we can conclude that the system has a unique solutions. Thus, the linear combination C1V1 plus C2V2 plus C3V3 is unique. All right, we just show that. Even though the calculation is the same, the procedure is slightly different because we try to answer different questions. Okay. Now let's move on to Theorem 2, basis and linear dependence. So if S consists of the vectors v1, v2 up to vn is a basis for a vector space, then every set containing more than n vectors in V is linearly dependent, right? Because the new vector that you add into this set, right, is redundant vector, right? Because you just need to that many vectors, those many vectors, to form a basis for a vector space. Now, if you add an extra vector into the set, then the extra vector is redundant. For example, if you have the standard basis set, that consists of I and j, right? You just need 2 standard unit vectors in order to form the basis for a 2-dimensional plane, right? Now, if you add an extra vector, that is the vector, let's say the vector 2, 2, the extra vector is redundant. You don't need that vectors to form the basis, right? You already have the standard basis. So that's the quick example to illustrate this theorem 2 on the basis and linear dependence. If you need n vectors to form a basis, then the n plus 1 vector is redundant. Okay. Now, Theorem 3, the number of vectors in a basis. If a vector space V has one basis with n vectors, then every basis for V has n vectors. Okay, so let's go back to example 1 and example 3, then example 2 and example 4. So in example 1, you have this standard basis has 2 vectors, right, that form the basis for R2. Then if you find all the non-standard basis for R2, the number of vectors in the set should be 2 as well. Okay, if now go to example 3, you can see this set has 2 vectors, and this set also a basis for 2-dimensional plane. Of course, not all sets can form a basis, right? Again, if you have a set and you know if the set is a basis of the vector space or not, you need to check two things, right? If the set span the entire vector space and S is linearly independent or not. All right. So now go back to example 2 and example 4. So you have the set S, where it consists of 3 vectors. This set is the basis for R3. Okay. Therefore, if you have another set that is a basis for R3, the set should consist of 3 vectors that you're going to see in example 4 here. So in this set, you have vectors 1, 2, 3, 0, 1, 2, and negative 2, 0, 1. 3 vectors that form a basis for a vector space R3. All right. So in example 6, we help okay. So example 6, problem A, you have a set with only 2 3-dimensional vectors. So this is not a basis. So S is not a basis for R3 since the set has less than 3 elements or 3 vectors. So the number of the vector in the basis for R3 has to be 3 vectors. In this case, you only have 2 vectors, so therefore S in this case not the basis of R3. Now problem B, you have 4 vectors, so this set is also not a basis of R3. So S is not a basis for R3 since the set has more elements than 3 or more than 3 vectors. Okay. And if I give you a set of 3 vectors, then it's possible that the set form a basis for R3. You just need to again follow the procedure to check if the set span R3 and if the set S is linearly independent or not. Now the last topic here is that the last theorem is that for any vectors v1, v2 up to vn in Rn, the following conditions are equivalent. If the set v1, v2 up to vn is a basis for Rn, then the set is a spanning set for Rn. And the set is linearly independent. So you have definitions, kind of the procedure to check if the set is a basis for a vector space. Now in this theorem, we have equivalent statement or equivalent conditions on determining if if a set is the basis for a vector space. Yeah. So if you have a collections of vectors you put in that set, and that set, if you already go through the procedure that the set is a basis for a vector space, then the following conditions are true. Right? So that's it for me in terms of basis for vector space. At the beginning, I talk about the application of basis for vector space, why we need to understand this kind of thing, and we go through definitions for basis for vector space, and we work on some example to determine if a set form a basis for a vector space. Okay. So again, the idea for two-dimensional plane is that you have a standard basis consists of I and j. For three-dimensional space, you have a standard basis consists of the vectors I, j, and k. And those vectors help you illustrate or demonstrate a two-dimensional plane or three-dimensional space in a rectangular coordinate system. But you don't have to always have rectangular coordinate system. Often you need a non-rectangular coordinate system, and when those are the cases, then you have a non-standard basis. Okay. Uh, when you are given a set, you have to count the number of vectors in the set. Is that less than the number of required vectors? Right? If in R3 you need at least you need to have exactly 3 vectors. If the number of vectors is less than 3, then the set you are working with is not a basis. If you have more vectors in the set, and then the vector of the set is not the basis. So in R3 you need 3 vectors, in R2 you need 2 vectors, R4 you need 4 vectors, and so on and so forth. No matter what the space you're working with, you need to check that the set span, the vector space, and the set is linearly independent. Okay, so that's it for me today. I will send out another video on dimension of the vector space later.